We talked about Lewis structures for ionic compounds, allowing us to illustrate the transfer of electrons from a metal to a nonmetal. Drawing the Lewis structure for covalent compounds allows us to illustrate the sharing of electrons between two nonmetals. We start out the same way we did before, drawing the element symbols, the individual element symbols, and their valence electrons. So the Lewis dot structure for the individual elements. The trick here is when we have more than two atoms in the compound. For a covalent compound, when this is the case, we need to locate the element that has multiple unpaired valence electrons. That's the key. That's going to become our central atom, and we're going to build out from there. So I chose H2O as our example here for a reason. There are two hydrogens and one oxygen, which means we have more than two atoms. We start by drawing the Lewis structure for hydrogen with its single valence electron. We move to oxygen with its 1, 2, 3, 4, 5, and 6 valence electrons. You can see here, it's clear that oxygen has these two unpaired valence electrons. That's the one that has the ability to become the central atom. It can bond in multiple directions. Hydrogen can't. So we take our remaining hydrogen and put it below. I'm going to put it adjacent to that other unpaired electron for oxygen. And now, instead of showing a transfer like we did before for ionic compounds, since ownership isn't lost or gained in this case, we're not going to show that. Sorry if you drew that in pen. I apologize. I should have erased it quicker. We're actually going to show the electrons. We say we pair them up. And I know that sounds kind of odd because electrons are negative, so it wouldn't seem logical for them to pair up. They'd repel each other. We say that it makes it easier for us to understand and visualize. So then we can condense this, make it a little bit neater, and we'll say it would be oxygen dash dash hydrogen, hydrogen, and then we fill out the rest of oxygen's valence shell. And this would be our clean and neat Lewis structure for a molecule of water. Important to note, we don't use brackets and charges, we use dash lines. For ionic substances, we don't use dash lines. For covalent compounds, the dash lines indicate what we call a shared pair. We're pairing up all the unpaired valence electrons. And there are three kinds of shared pairs. If you see one dash line between two atoms, as you do here, in fact, the entire molecule of ethane here, it's filled with nothing but what we call single bonds. One dash line between atoms. And a single bond means you've got an electron here, an electron here, making up one shared pair. That's the case in all four directions for carbon. It has single bonds between itself and all the hydrogens and a single bond between itself and the other carbon. Important distinction here. When you have a single bond, the number of electrons being shared is 2. The other way you'll be asked about this type of bond is the number of electron pairs being shared. That's 1. Right, when we get to double and triple bonds, you'll see we need to keep track of not only the number of electrons, but the number of shared pairs. You'll see it show up on the Regents. It comes up every year. You have to be very careful about reading is whether or not they're asking you about the number of electrons or the number of pairs of electrons. When you see 2 dash lines, that illustrates a double bond. Now what we're saying is you have 1, 2 electrons, 3, 4 electrons. 2 pairs of electrons are being shared between the carbons. And this is something that's very unique about carbon, since it has 1, 2, 3, 4 unpaired valence electrons. That means it can form 4 bonds. And when you have 2 carbons next to one another, that would illustrate two shared pairs. In this case, hydrogens filling out the rest. A little compressed there. So when you have a double bond, now the number of electrons being shared is 4. The number of electron pairs being shared is 2. And this is one of the things about carbon, makes it very special, and allows carbon to form chains and rings, because it can form multiple bonds in multiple directions. Very important to remember that.